Effect is a TypeScript library that gives you the tools to make it easy to write complex applications in a safe and composable manner. This video is a detailed introductory guide to the core effect concepts. We'll start with the basics, then move on to slowly build an example program piece by piece, which by the end will feature concurrent asynchronous work, granular error handling, dependency injection, and benchmarking. If you're still curious about why effect is worth learning, feel free to check out my other videos on effect linked in the cards now and come back after. Effect is an amazing library, and I want to quickly thank the Effect team for financially supporting the creation of content around it. Now, onto the tutorial. First, make sure to add the Effect package to your project using your package manager of choice. With that out of the way, let's get to business. We'll begin with the Effect type. This type is the center of the entire Effect ecosystem. The Effect type is generic over 3 parameters which describe its behavior: requirements, error, and value. You should conceptualize an effect as a function that takes in its requirements as an argument and returns either a value or an error. It's important to emphasize this function-like nature of an effect. Just like creating a function doesn't execute its body, constructing an effect doesn't execute its content. We could say that an effect is a description of a program. The output value is computed only when the effect is ran. The unit effect is the most basic effect type. It describes a program that has requirements of type never, meaning it does not have any dependencies. It also has an error of type never, meaning it will never err, and has a value of type void, meaning it does not return any value. Let's break down this effect. Like the unit effect, its requirements field is never. However, unlike the unit effect, its error is of type error. This means that the effect may fail with an error object. The final value type is number, meaning this effect will yield a number if it succeeds. To create an effect from a value, we can use the succeed and fail constructor functions. Succeed takes a value and returns an effect that can only ever succeed with that value. Along the same lines, fail takes a value and returns an effect that can only ever fail with that value. The power of the effect type comes from its ability to compose together with other effects. Here is a basic division function. First, it checks if the divisor is 0, and if so, returns an effect failure containing an error. Else, it returns an effect success containing the result of the division. In the return type is where the magic happens. See how both the success case and the failure case merge into a single type that describes both outcomes? It is now abundantly clear that a result of this divide function is an effect that when run will yield either a number or an error. Remember how an effect represents the description of some behavior to be ran at a later point? Well, when we use the succeed and fail constructors, the value passed to them is evaluated when the effect is constructed, not when it is run. However, when working with code that has side effects, it might be important to defer those side effects until the effect is run. To do this, we can use the sync constructor. Sync returns an effect with a value of the return type of the passed function. But this function is only ran when the effect itself is ran. Here, this effect represents a program that when run will log to the console and return a number. It's important to note that sync always returns an effect with an error of type never. This is because the function passed to it should be guaranteed to never throw. However, non-effect code will throw errors, and that's okay. The try constructor catches errors thrown from the passed try function and passes them to a catch function, where you can construct the value to place in the error channel of the resulting effect. Here, JSON.parse will throw if the input is invalid JSON, such as this empty string. If so, we create a new error with a custom message. Like sync, the resulting effect has a value of the return type of the passed try function, in this case any, and the error is of type error, the return type of our catch function. To model an asynchronous computation, we can use the promise constructor. Notice how the resulting effect returns a number and not a promise of a number. This is because effect handles the asynchronous aspect for you, so you only have to worry about the resulting type. Just like with sync, it's crucial that the promise returned from the function passed to the promise constructor never rejects. If it might, just like the synchronous version try, we can use try promise to handle rejected promises with a catch function. Well, this is great. We have a bunch of effects, but we have to run them for them to do anything. To do this, we can use the two basic run functions provided by Effect. To run an effect synchronously, we can use the run sync function. This will run our effect, triggering any side effects in the process and returning a value of the value type of the ran effect. If the effect fails, or if any asynchronous tasks are performed, the run sync function will throw an error. To run effects with asynchronous computations, we can use run promise, which will return a promise of the value type of the ran effect. Just like run sync, if the ran effect fails, the returned promise will reject. Running effects should occur at the edges of your program when you have no other choice but to run an effect. While you're within effect code, Effect provides tools for you to manipulate the values inside an effect without needing to run it. Before we discuss the specifics of these transformation functions, it's important to stop and explain pipe. Pipe is what allows us to seamlessly carry out one transformation function after another. It takes a value and a series of functions and applies them one at a time. This is best shown with an example. Here we have three functions which each take and return a number. Using pipe, we apply them one at a time, feeding the output of one as the input to the next, and ending up with our final result. Pipe allows us to use functions in a clear, left to right, or top to down order instead of confusing deeply nested function calls. For convenience, the effect type also has a pipe method, which is identical to passing the effect as the first argument to the pipe function, but can look a bit cleaner. I'll mainly use the pipe function throughout the examples in this video, but just know both the pipe function and the pipe method are the exact same, and you can use whichever way works best for you. The map function is simple. It applies the function passed to it to the value inside an effect, and returns a new effect whose value is the output of that function. In this example, the function passed to map takes in a number, in this case the one value from the previous effect, and converts it to a string. When we log the result after running the effect, we can see the output is a string 1. Let's recreate our divide function from earlier, but this time with the input as a single object so it can be the singular value of an effect. Just like earlier, our mapping function will either error with an error or succeed with a number. Well, this sure isn't what we wanted. Our effect has a value of another effect. What we really want is for the effects to merge, carrying the new value type from the output of the mapping function while combining the possible errors. To do this, we can use flatmap. Flatmap takes a function that accepts an input whose type is the value of the previous effect and returns a new effect. The result of the flatmap will be an effect whose value is the value of the effect returned by the mapping function, in this case, number, and whose error and requirements are a combination of the new and previous effects. Let's take a look at a short example using what we've learned so far. To start, we'll define three values. The first, getRandomNumber, returns an effect that always succeeds with a random number between 1 to 10. We use effect.sync and not effect.succeed because the generation of a random number is a side effect. Next, checkIfAtLeast5 is a function that returns an effect that fails with type error if the number is less than 5, or succeeds with the passed number if it's greater than 5. Finally, logNumber uses effect.log to create an effect that represents the logging of the value to the console. We'll talk more about logging later in the video. Our program will start with the getRandomNumber effect. It may feel strange to see the generation of a random number as a value and not as a function. But remember, this value is an effect which represents the computation of this random number, which is lazily evaluated. This means that the same effect value can be used in multiple places, as it triggers the internal side effect each time the effect is run. Next, we'll apply a map function that multiplies the number by 2. Then, we'll flatmap with the checkIfAtLeast5 function. Notice that the type of our program now contains the error from that function. Finally, we'll flatmap with our log function. The final type of our program is effect_never_error_void, meaning it either fails with type error or succeeds with type void. What if we want to cause some side effect but still have access to the original value after? We can do this with the tap function. Tap is just like flatmap, but the result of the function passed to it is ignored, and the original value is still available for the next function. This is useful for executing side effects without altering the result of an effect. So far, we've only been working with single values, but what about transforming the results of multiple effects? For this, we can use all. All takes an array of effects and returns an effect whose value is a tuple of the values of the past effects. Here in this example, we merge foo and bar to a single effect, then run and log it. Alternatively, all also accepts objects where the values are effects. And that's all that we need to get started on the example program we will make and then improve over the rest of the video. Our program will look like this. First, we'll generate some random numbers. Then, using the numbers as IDs, we'll get information about the Pokemon with that ID from an API. Next, we'll validate the return JSON. And finally, we'll calculate the heaviest Pokemon and log it. Our program will start simple but naive, and we'll add robustness bit by bit. We'll start with a function to get the Pokemon data from the API. We're using try_promise to wrap the fetch call because it might reject. However, the value of the resulting effect is any. We should validate what type it is. Effect has a first-party validation library called schema, which we will use to validate the shape of the data returned from the API. We define our schema as an object with a string name and a number weight, then derive a type and validation function from this schema. This video won't cover schema outside of this one use case. Just know it exists, can be used for validation, and works seamlessly within the effect ecosystem. Be sure to check out the schema GitHub README for more information, and look out for a video covering it from me in the future. We can pass the result of the fetch plus JSON effect to the parse Pokemon function combined with flatmap to validate it. Now we can see that the returned effect contains a Pokemon, as well as a potential parsing error being added to the error channel. Next, our random array function. It will generate an array of 10 random numbers between 1 and 101. First, we fill the array with an effect to generate a random number. Then, we use effect.all to convert the array of effects to a single effect with an array of numbers. Now, we can start our program as a pipeline beginning with the random number array effect. Then, we take that array and map it with our getPokemon function. This returns an array of effects, so once again we use effect.all to end up with a single effect containing an array of Pokemon. Then, using run_promise, we can run the program to trigger all the effects and return the Pokemon array to log to the console. After running our code, assuming that none of the fetch or validation operations failed, we should see all of the data printed out. Then, to clean things up a bit, we'll add a simple format Pokemon function to map our Pokemon array with, and use effect.log combined with effect.tap to trigger this side effect. To calculate the heaviest Pokemon, we'll create a new function that takes an array of Pokemon and uses effect.reduce, which is like the normal array.reduce, but where the reducing function returns an effect, allowing for error handling. In this case, if two Pokemon have the same weight, we'll consider that an error, and return an effect failure containing an error. Then, we can add this to the end of our program, flat mapping with our calculate heaviest Pokemon function and logging out the result. This time with flat map instead of tap, as it's fine to consume the number as this is the final part of our program. The type of our entire program is effect never error void, meaning it takes no requirements, may error with some error object, and returns no value on success. And when we run it, it does what we expect. Now we're going to talk about effect generators, an optional way to write your effects in a more familiar way. Just like async await allows us to write asynchronous code in a synchronous looking way, generators allow us to write effectful code in the same familiar manner. Using generators looks like this. First, pass a generator, that's the function star, to the effect.gen function. This generator takes one argument called an adapter, which the common convention is to alias with an underscore. Whenever we want to extract the value of an effect for use in our function, all you need to use is yield star adapter. This evaluates to the value within the effect, while automatically propagating any errors or requirements from that effect to the effect returned by effect.gen. Other than that, just write your logic as you normally would and return the result. Remember this example from earlier? Let's convert it from using pipe to using generators. Now we can assign values to variables and manipulate them just like normal. Previously, where we used effect.flatmap, we now use the yield star adapter pattern, and effect.map just becomes regular code. Generators are just another way to write your effects. You can use them nowhere, everywhere, or in between. Whatever style works best for you. Now let's see what it would look like to use generators in our Pokemon program, where previously we used pipe. Our new getPokemon function looks like this. First, we yield the value from our fetch try_promise effect and assign it to a variable. Then, we pass that to the parsePokemon function and yield, then return the result. In our main program, we yield each effect, assigning the result to a variable if there is one. Errors happen, but if we can account for them, our code becomes much safer. If you've watched my previous effect videos, you know try-catch is a massively flawed error handling strategy. Effect, on the other hand, treats errors as first-class citizens, allowing them to be fully type-safe values that could be the result of an effect. Up to now, we've been using native error objects with messages as our errors, but effect's error handling becomes really powerful when you define your own error types. In normal JavaScript, the convention is to extend the error class, but this is not required when using effect, just a plain object type that defines the contents of the error. To prevent TypeScript from unifying types during inference, and to identify types at runtime, effect commonly uses an underscore tag field with a unique string name for that type. Using classes is a really convenient way to define a type and a constructor function for that type at the exact same time. This is also a very common pattern in effect. So, we have effects with errors, but what tools are available to deal with those situations? To handle every possible error case, we can use the catch_all function. This takes a handler function, which takes the error as an argument and returns an effect to become the new value in case of any error being present. After using catch_all on our example effect and returning an effect success, the new error type is never. To catch a specific type of error, we can use catchTag, whose first argument is the string tag of the error to catch. All other errors will still remain in the error channel, such as the divide by zero error in this example. As an alternative to using catchTag multiple times, the catchTags function allows you to pass an object where each key represents a tag, with its value being the function to handle that error case. In effect, errors short circuit. This means that the execution of the happy, error-free path ceases immediately when an error is encountered. This example demonstrates that behavior. Since operation 2 fails, the console log of operation 3 never gets executed. Now, let's modify our Pokemon program to handle errors where we previously ignored them. We'll start by modifying our getPokemon function. It has two possible points of error, the response promise rejecting and then the JSON promise rejecting. Previously, we caught both errors under the same generic error object. However, now let's make them distinct. To start, we'll define our new errors as classes. These don't need to contain any additional information. Their identifier alone is enough. Now, we can separate the fetch call and the JSON call into two separate try_promise effects, which each fail with the respective error type. Now we can see that the resulting effect contains all three possible errors that could occur. Next, we'll create a same weight error for the calculate heaviest Pokemon function. It will contain the weight that the two Pokemon share. Now we can see that all of our errors have made their way to our final program effect. We want this program to never fail, so let's add logic to handle these errors. To start, we can catch the same weight error and log out a message. However, the errors from the getPokemon function are still there. To handle this, at the end of our pipeline in our getPokemon function, we can use catch_all to handle every error case and return a default implementation of our Pokemon type. Now, the error type of the returned effect is never. After these changes, our entire program now has an error channel of never, meaning we can be sure it will never error. In generators, code generally represents the happy path, so we can add error handling at the end of our generator. Here's what the gen version of our new getPokemon function looks like. We create the variable for response in JSON, yielding the effects like before. At the end, we use the pipe method to pass our catch_all functionality. We can do a similar thing for our program effect, adding our catchTag functionality in the pipe method after the generator. One other option here would be to use effect.either to make the value yielded either the value or an error. Then, use an if-else block to handle both cases. logging the error message if the value is an error, and the successful message if it's a Pokemon. Currently, our Pokemon app is hard-coded to fetch data through a fetch call to a specific API. But what if we wanted to get the data from a different API, or a database, or maybe even add a cache layer within our application to check before making an API call? To do this traditionally, you would have to refactor your code on every chain. But what if we could pass the signature of the data fetching to a dependency that we pass to our effects and could change the implementation of higher up the chain? Effect provides this behavior through the requirements field of the effect type, which we have ignored up till now. Let's take a look at a simple example. First, we'll define the type signature of our dependency. Here, it will be an object with a unique tag and one other property, next, which is an effect never, never number. Like earlier, effect is noticeably not a method because effects are lazily evaluated. Every time next is run, a new number will be yielded. Then, we'll import the context module from effect and use the tag function, passing the type we just created as a generic. A tag is a unique identifier that represents a dependency of some generic type. A unique string argument is passed to ensure the identifier generated is always the same. We can use the tag just like any other effect, here piping it through flatmap. Within the flatmap function, we now get access to the value of type random, where we can use the next attribute. Notice how the random type now appears in the requirements field of the resulting effect. If we try to run a program with a requirements field that is not of type never, we get a type error. Effect is ensuring that we provide any dependencies required for our program before it can be run. To do this, we can use the provide service function. It takes the tag and a value that fulfills the type of that tag. After we provide the service, notice how the requirements field has gone back to never, meaning this effect can now be run. Let's apply this concept to our Pokemon program. We'll start by defining the type signature of our client and its tag. It will just have one method, getById, which will take a number and return an effect containing either a Pokemon or the possible errors from before. Our getPokemon function now looks much simpler as the data fetching logic has been abstracted away. We use the client tag and call the getById method, and they catch any errors with the default Pokemon. After doing this, the Pokemon client type has appeared in the requirements field of the resulting effect. Now, in our main program, we can provide the Pokemon client implementation before passing the result to run promise. Here, our implementation of the getById method is identical to the logic of our getPokemon function previously. But now, we could change the data source or add caching, and our downstream usage of the client doesn't need to change at all. With generators, we get the client by yielding the tag and return the yielded result of getById. Then provide the service the same as we did just now in the pipe version. Our final topic will be logging. Effect provides a powerful set of logging tools to use to observe your program. As briefly introduced earlier, the log function logs the given message to the console along with some additional information and returns a void effect. Effect has different log levels that can be used to categorize your logs. You may notice that the log debug call was not printed to the console, and this is intentional. By default, all debug logs are not printed. Using the with minimum log function from the logger module, we can manually adjust this setting. In this case, we can lower it to now show debug logs, but you can also choose a higher minimum level as well. Our final topic will be on timing spans of your program. Using the with log span function, our logs will now include a timing of that span. Let's add logging and benchmark the timing of our Pokemon program. First, we'll convert our previous vanilla log when catching the same weight error to an error log. Then, we'll add a program finish log after the program is completed along with its own log span. After running, it looks like the program took around 450 milliseconds to complete. By default, effect.all runs effects in sequence, one at a time. In our case, this means that the next Pokemon fetch request waits until the one before it has fully completed. We can speed this up by running the effects concurrently all at the same time. In effect, this is as easy as adding concurrency unbounded as an additional argument to effect.all. This argument can also take a number if you want to set a specific concurrency limit. Running it again, And with just that one change, we've cut the time in half. Pretty cool. Program complete. Let's recap. Effects are immutable values that describe some operation to be executed when the effect is run. Any side effects present in the effect are only triggered when the effect is run. An effect may require some dependencies before it can be run, and when run will produce either a value or an error. To create effects from values, we can use the succeed and fail constructors. To create effects from a function, or any operation that triggers side effects, we use sync or promise for asynchronous effects. If these operations have any chance of failing, we must use try or try promise to absorb these errors into the resulting effect. Effects should only be run at the edges of our program when required to finally yield a value. For purely synchronous effects, we use run sync, and if even a single effect contains asynchronous code, we must use run promise. Most of our effect code will take place in pipes, where we can transform the value through multiple functions. We can manipulate the values inside of an effect with map and flat map, trigger side effects with tap, and combine multiple effects with all. Generators are an optional way to write logic in effect that is similar to async await for promises. It uses the yield star adapter function pattern to unwrap the value from an effect while still bubbling up any errors. Errors in effect stop the execution of the happy, error-free path immediately. They most often take the form of objects with an underscore tag field to discriminate them. To catch errors present in our pipelines, we can use the catch functions to choose what errors to handle and how to recover from them. We can create dependencies for our effects by defining a tag for some type and using it in our effect. We must then provide an actual value of that type before our effect can be run using effect.provide service. Finally, effect provides 5 different levels of logging with the ability to modify what levels are actually written out to the console. And using the with logspan function, we can time portions of our programs. These are just the most basic concepts in effect. The iceberg goes way deeper. But don't feel overwhelmed by effect size. Focus on learning the most commonly used functions and patterns, and move on to the more advanced stuff when you're ready for it. This video is just a starting place for your journey learning effect. The effect docs are the next best place to go from here. You can review the concepts in this video in the Effect Essentials section, or move on to other things you find interesting. The Effect API reference sites can also be a helpful resource to check out. Finally, the Effect Discord is a great community of Effect developers that want to help you learn, so consider joining. Links to all of that and a GitHub repo containing every snippet in this video, along with the Pokemon example program at each iteration, is available in the description. And once again, thank you to the Effect team for sponsoring this video. If you enjoyed this video, consider subscribing. As always, the transcript and markdown source code are available on my GitHub, link in the description, and any corrections will be in the pinned comment. Thank you for watching, and I'll see you in the next video.